Well, in this screencast, having conquered derivatives and areas, all that remains are arc lengths. When we graph a polar curve, how long is that polar curve? And we again borrow an idea from parametric curves. We know that an arc length is going to be an integral of a square root of the derivative of x with respect to the parameter squared plus the derivative of y with respect to the parameter squared. When we graphed parametric curves, this is what we did. We took dx dt squared plus dy dt squared, big square root dt from a to b. Well, the only thing that's changed is that the parameter is now theta, and we go from alpha to beta because that's what thetas do. Well, what does that mean? We know what dx dt, what dx d theta is because we've done the product rule a bunch of times. Dx d theta is negative r sine theta plus cosine theta dr d theta. And we know what dy d theta is because we've done the product rule before. R cosine theta plus sine theta dr d theta. And so now it's just algebra. Now, when we do the algebra, and I won't, when we do the algebra, a bunch of things cancel out. There's a lot of terms here that are the negatives of terms over here, and they cancel, leaving behind an r squared times sine squared theta plus cosine squared theta. And then there's a dr d theta squared times a sine squared theta plus a cosine squared theta. Now I know what you're thinking to yourself. I know what that is. I know what that is. Both of those are 1. And you're right, which means that arc length of a polar curve is the integral from the first theta to the second theta of square root of r squared plus dr d theta squared d theta. That is how we find the arc length of a curve graphed polar. And so let's practice. Let's find the arc length for r equals e to the theta on the interval from 0 to pi. Well, arc length is an integral from 0 to pi of the square root of r squared plus dr d theta squared. This part's r. This part is the derivative of r with respect to theta. Well, that's not too bad, right? I mean, this is the square root of 2e to the 2 theta. Well, that's a square root of 2. Pull that out. And the square root of e to the 2 theta is just e to the theta. So we know how to do that. We take an antiderivative, sub, and subtract. Substitute pi, substitute 0, and we got it. We have an exact length for the polar curve. Now, this happened to be really easy, fairly straightforward. In a lot of the questions that a Calculus 2 student does, all the Calculus 2 student can do is set it up, and then a calculator's got to take you the rest of the way. One more. Let's find the arc length of r equals 1 plus cosine theta on 0 to 2 pi. So how does arc length go? It's an integral from the first angle to the last angle of the square root of r squared plus dr d theta squared d theta. This is the r. This is the derivative of r with respect to theta. Now, this is workable with some trigonometric work. I'm not going to work it out that way. I'm going to suggest that you make sure that your calculator can do this. And it won't matter to your calculator if you call these thetas or t's or x's or whatever. Your calculator doesn't care what that variable is. You should make sure that your calculator gives you an arc length of 8. And that's important because we should know how to make our calculator do this. We should know how to set it up and how to make a machine give us the answer that we want. And that'll be important too as you're doing the extra practice questions that are available in our course. Okay, that's all I want to say about arc length, and I hope that this is a good push in a good direction for you.